All right, dear students, today we're going to be talking about water and its role in nature and life. Water is really essential when talking about the creation of life. Most of our cells are going to use water. There are some proteins like digestive enzymes that use water in more than the 85% of their functions. Okay. So let's see. Water. So all living organisms require water. Enzymes, biological molecules that we use that increase the rate of chemical reactions need to be dissolved in this universal solvent that is called water. So in water, it provides different stable medium for life processes to operate. Okay. So Earth is 71% water, mostly in oceans, that is 97% of water, and only 3% is fresh water. Water has existed for 3.8 billion years, almost as long as the Earth planet, that is 4.5 billion years. Life originated in water, where oceans shielded early cells from ultraviolet radiation. And living organisms are 65 to 95% water by mass, and about 80% of human cells is water. Water's unique properties enable life from the single bacteria to the biggest tree. Without it, they would not exist, including you or me. Okay, so there are some concepts that I would like to point out today, and they are covalent bonds. So remember that we have three different types of bonds. Generally speaking, we have the covalent, we have the ionic, and metallic. Okay, and here in the covalent, we're going to find non-metals bonding non-metals. Okay, in ionic, we're going to find a metal plus a non-metal. In metallic, there are going to be two metals, right? So non-metals and non-metals are going to be covalent, and they can be polar covalent, or they can be non-polar. The water molecule is a polar covalent because there is an imbalance, in their molecules. Okay, so there is an unequal distribution of electrical charge. One end is slightly positive and the other one is slightly negative. Hydrogen bonds, they are going to be a weak, attractive intermolecular force. And when I say intermolecular, I mean between molecules, among molecules, right? So a hydrogen atom in a molecule is attracted to an electronegative atom, such as oxygen, in a different molecule. So I'm going to show you how it happens. So as far as you know, the water is represented by H2O. When I say H2, I mean that we have two hydrogen atoms, and they are going to be partially negatively charged. And that's represented with this delta positive. Delta positive means that they will be partially positively charged. In the oxygen case, we have a partial negative charge. It will be partially negatively charged because its electronegativity value is higher than that one that is present in the hydrogen. So one oxygen atom combines with two hydrogen atoms by sharing pairs of electrons, and this is covalency. So when you share electrons, you talk about covalency. That is a covalent interaction, right? Is sharing of electrons. The oxygen nucleus draws electrons negatively charged away from the hydrogen nucleus positively charged. So there is going to be like an attractive force presented here, and the electrons that were contained by the hydrogen are going to be attracted towards the oxygen. Okay, same would happen in this case. So this electron will be attracted by the oxygen. Okay, so if you go and you check your periodic table, the oxygen's electronegativity value is higher than the hydrogen. That's why it is attracting the hydrogen electrons with more intensity. And when I say this, I mean that electronegativity is related to the capacity or ability that an atom has to attract other electrons from external atoms that are forming molecules with them, right? So that capacity is basically related to the number of groups. For example, if I have a fluorine that is in a higher group than that one that is in sodium, obviously fluorine will have more electronegativity, right? Because its group that represents its valence electrons is higher than that one that is in sodium, right? The same happens with chloride, sodium chloride, right? So chlorine, that is an atom with more electronegativity, will have more capacity to attract other electrons that are in the other group, that is group number 1. But that was something to explain you. Let's go back to the water. So the water molecule carries an unequal distribution of electrical charge, even though overall, if it's electrically neutral. That will become this in an imbalance. And when there is an imbalance, I'm talking about something that is polar. Let me illustrate this with other example. For example, if I have like a magnet, and my magnet will have a positive charge and the negative charge. So that is going to be polar. That's what we call polarity, right? Polar. The Earth planet, for example, it contains two different poles, right? We have the North Pole and the South Pole. Okay, so this also is going to be polar. That's why we call them poles. Okay, so when it happens, it becomes into a polar water molecule. And there is electrostatic attraction between positively charged regions of the water molecule and the negatively charged regions of a neighboring one. So giving rise to weak bonds that we're going to be calling hydrogen bonds. Okay, so when this happens, when you form the water molecule, right? So it has like the negative region here and the positive regions here. We're going to form something that is called an interaction that is called hydrogen bond, right? So this water molecule is going to be basically having negatively charged, negative charge oxygen, positive charge hydrogens, okay? Positive, and this will make the interaction between positive and negative. They will attract one to each other slightly, I mean. So these hydrogens will be here like containing positive charges, and that's what happens. So if you go and you look, something that is called the Coulomb's law, when you're going to observe that in the Coulomb's law, we say that Coulomb's constant times the charge 1 times charge 2 over square radius, right? Remember, this is a Coulomb's law. And the Coulomb's law states that similar charges repel, so we have a repulsion process here, while opposite charges are going to attract, okay? And that's what's taking place in this case. So the water molecule in the hydrogen bonds, it forms is stated here. So as a reminder, water molecules consist of one oxygen atom and two hydrogen atoms bonded by shared electrons, and they are called covalent bonds. The molecule is V-shaped, and the water molecule will present an angle of 105 degrees, right? So if you reduce or increase that angle, the water properties will not be the same, right? In fact, there is an experiment that was performed in the United States to check the probability to have the same properties, and basically the results were a disaster. So the angle of the water molecule must be that way, because if not, it doesn't work at all. I mean, the hydrogen bonds in cohesion and all the properties are not going to be basically working, right? So the V shape that is not linear with an unequal distribution, I mean, with a polarity, will be making it polar. And positively charged hydrogen atoms in one water molecule are attracted to negatively charged oxygen atoms in nearby molecules, forming hydrogen bonds. Hydrogen bonds are weaker than covalent bonds, but strong enough to hold water molecules together and interact with charged particle surfaces. And these bonds are key to water's unique properties. So there is a short activity that I normally ask my students to represent by using the delta charges, right? And I say delta is this, guys. Delta negative, delta positive, right? This means a partially negatively charged. And this other means partially positively charged. If you want, you can pause the video and represent the water molecules with hydrogen bonds and delta charges. Hydrogen bonding is given within water molecules, but it's really important to comprehend that the hydrogen bonding is basically given between molecules, right? And that's what we call an intermolecular interaction, okay? Because this is given between water molecules, right? And it's not given inside because there is another molecular interaction that is called intramolecular. Intra is different to inter. And inter means between. Okay? So really important to comprehend that hydrogen bonds are formed between water molecules, right? So do not confuse intra with inter. Computer models help scientists to understand how water structure was vital for its properties in life. So these scientists use here Lynden-Bell and colleges at Queen's University, Belfast, used simulations to study water, and they decreased the water angle. So they try to decrease the angle of the water molecule by an angle of 90 degrees, right? And they also weakened the hydrogen bonds by 50%, right? So what they discovered was that if they perform this experiment with water molecule, obviously they use computer science to perform this, to make this experiment. They discovered that the water properties were going to be altered. So we have the pseudoscience and the memory of water. It's confirmation bias. So pseudoscience basically is something that is not supported by the scientific community. So it lacks rigorous methods such as the scientific method. So in this case, I'm bringing to the table something that is called a homeopathy claim, that it stated that water retains a memory of substances after dilution. So it means that if water had been in a solution with another compound, the water will retain those compounds' properties, right? So water will be acting out as a solvent in this case in the compound, or other substance will be acting out as a solute, no? So basically that the homeopathy stated was that the water could retain those other substances' properties by certain period of time. But what we discovered that it lacked rigorous methods, especially the scientific method. So, and they also, in pseudoscience, are only looking or seeking supporting evidence, right? So remember that in science, we have the scientific method. It's a word that was formed by two languages, right? So we had the Greek language and we had the Latin language. So we have epistemonikos, right? Epistemonikos. Epistemonikos, that means science or knowledge in this case. So this word comes from the root epi, meaning upon or over, right? Stemi, meaning to stand or to settle down, to establish, right? Epistemonikos. And we also have the other word that is metros. And metros, in this case, this is like metros, right? Means it comes from meta, no? Meta. Right? So this means after or beyond, right? And odos, that is this other one. This means way or path, right? Is basically the way toward, right? So the scientific method can be understood as epistemonic methods, and that refers to search a path to acquiring or establishing scientific knowledge, right? So in the scientific method, we're going to have different steps, okay? And those different steps can be, for example, the first step we got to follow in scientific method is the observation. The observation, and after you have observed a phenomenon, sorry, that is natural, and that will raise you questions, right? So then you have to question, you have to formulate a question. Then you're going to make a hypothesis, right? And the hypothesis is basically something that can be true or that can be false, but it's something you believe in, right? After that, you'll have to design some experiments to test your hypothesis, right? So the experiment is basically to test if your hypothesis is true or is a complete hoax, no, is false. I mean, so then you're going to have the data collection. You can say data collection or data collection, as you want to say, right? Data collection. And then you're going to analyze right? And this is where I invite, to do when we are like taking a science course, right? So you have an analysis, you analyze those data, right? The data information, and then you're going to conclude. You're gonna go into the conclusion, right? Conclude, and then you're going to design a report on what you found, right? So basically, those are the different steps you have in the scientific method. So let us approach these steps. So first, the observation, right? So then you're going to ask a question about it. You create a hypothesis, right? Then you perform an experiment, right? So then there is going to be something that's called data collection. You're going to record the observations and measurements during your experiment. Then you're going to analyze that information. You're going to wound up to a conclusion. And finally, you will report it, right? And those are the steps that we have when talking about the scientific method. Right? And method, remember that it came from two languages, right? That is Greek and Latin, right? So basically, epistemologos methodos. This is what we propose in this. But in this case, in the case of pseudoscience, they lack evidence, right? So that is gonna basically skip the scientific process. So the confirmation bias is basically the tendency to favor information that supports existing beliefs, but does not go with rigorous scientific procedures. Okay, and finally, okay, the water memory refuted. Those tests that were taken by these scientists that's called the Benveniste's team in obviously in he basically they were like not replicable because there was another group from the nature community that is an older scientific community is called Nature. So there is in fact there is a magazine that is basically performed and undertaken by this older community, and they were testing the Beminist experiment. It didn't work, right? So scientific evidence didn't support the idea of water having those chemical properties of the previous solutions that had been conforming, okay? Okay, so in here, we're going to find other two properties, and there is an important property that is called cohesion. Cohesion is a force by which individual molecules of the same type attract and stick together, right? It's really different to that one that we know as adhesion, right? So normally people misunderstand these two concepts, right? Cohesion is basically the force, right? That's going to be attracting and sticking water molecules. Okay. At the same time, we have another type that is called surface tension. So surface tension is basically a property that will allow that water resist an external force, right? So this is due to the cohesion between water molecules. So these two are closely related one to each other. Okay, so let's see what's next. Okay, so cohesion of water molecules and impact on organisms. So here you can find, for example, this plant. And okay, so thanks to cohesion, water molecules are going to stick together and they will form a strong cohesive force, right? That's why, for example, when you see that it's raining, you're going to see that the water droplets will have this spherical form because basically we have different water molecules here sticking one to each other, right? They are like bonding one to each other. And that's what happens in this case. So if you analyze this drop of water, it contains like spherical shape. That's due to cohesion. Okay, so what's next? Water in plants. Also, cohesion will allow water to have allow plants to have their photosynthetic process, right? And cohesion will be working, allowing water to be drawn up through silent vessels in plants, right? So the water basically will be like going up, okay, through xylem vessels in plants, and that's going to be fighting in a certain way against the gravity force, okay? That is 9.8 meters over second squared in the earth, I mean. So the water molecules are going to be sticking one to each other, and they will be going outward until they reach out the lips, right? And they have the transpiration. So the transpiration is basically transpiration, right? They will evaporate, okay? So the transpiration process that is taking leaves is basically due to the cohesion force, right? Okay, so also we have the surface tension. So water has high surface tension due to the hydrogen bonds enabling the formation of spherical droplets. In hydrogen bonds, as we have said, they individually weak but collectively strong. So when we have, for example, if you say that a hydrogen bond is strong enough, it's not, right? But many hydrogen bonds are going to be strong enough to do many things, right? So they are going to give water its cohesive and surface tension properties. Okay, so here I have like a diagram explaining. So basically, we have the tree here, right? And the water is going to be taken by the tree's roots. So we're taking from soil by root cells, right? And water up to the tree trunk by force generating transpiration, right? Water is going to be drawn up the tree trunk, right? This using its silent vessels, right? Silent vessels. And basically those water molecules using the cohesive forces are going to be reaching the leaves, right? When they reach the leaves, okay, they will have the transpiration, completing the water cycle. All right, so water can be drawn up to a great height without the column breaking or pulling apart. Silent vessels run from roots, lips, as continuous narrow tubes. You can observe here, right? And the column of water coheres, does not break, adheres to the walls of the silent vessels and flows smoothly through them. A common mistake you can find here is that only one hydrogen bond is not going to be enough, right, to hold water molecules, but many of them, many hydrogen bonds can work in a better way, right? So they're going to be basically increasing their cohesive forces, okay? All right, so let's see what's next. Right, so talking on surface tension with cohesion in water. So cohesion, as we have mentioned, is basically the capacity that water molecules have to stick one to each other, right? Due to hydrogen bonding. But surface tension, we have to explain here something, is that the outermost water molecules form hydrogen bonds with molecules below, creating high surface tension, second only to mercury. So strong surface tension allows water to form nearly spherical droplets, like this one that I already explained you when it rains. But okay, so what about the surface tension? So you can see this insect is using the surface tension, but maybe the question is, why does not this insect sink? Why doesn't it sink? All right, so what I can tell you is that these are the first layer, this is the first layer of water molecules, right? This means this is the surface. In this case, these are the water molecules that this insect is in contact with. But we have other water molecules in the lower layers, right? So surface tension, in this case, the molecules at the surface will form stronger bonds like these ones that contain two arrows. And that means that this is going to be like a matrix in certain way to avoid that the insect sinks, right? So upon skater moving over the water surface, so the water surface tension in this case is going to support the pond skater, and the surface will be depressed by the hydrogen bonds holding together, okay? This is what happens in this case. Right, so this is an activity. If you want to solve these exercises, you can, but I'm going to keep going. Right, so there is a top tip here that the diffusion of molecules through a solvent, such as water, is inversely proportional to the viscosity of the solvent. So temperature affects the viscosity of liquids. For example, the viscosity of water at 25 Celsius degrees is approximately half than when the temperature is 4 Celsius degrees. As we will see in B2.1, the diffusion rate of molecules is extremely important for the processes that are needed to sustain life. So designing surface tension, this is another experiment. If you want to make it, okay, welcome. Okay, there is another common mistake about two terms that we're going to see, right? Heat capacity. Heat capacity is not the same as specific heat capacity, right? Heat capacity is the amount of heat that is required to change the temperature of a body by 1 degree. So the amount of heat energy per unit mass is needed to calculate specific heat capacity. So unlike heat capacity, specific heat capacity is therefore independent of mass or volume. Okay. So here we have the adhesion of water. And adhesion is a force that causes individual water molecules to clean the surrounding material. So I'm going to give you an example. Here I have this is a cylinder, right? And in this case, I'm gonna pour water in my cylinder, right? So you're going to see that if I pour water inside the cylinder, measuring cylinder, the water will have this form. And it can say 5 milliliters, right? Because the water is basically using its adhesion property. So the question is, what is the water's volume? What is the volume for water in this case? It's not going to be 7 milliliters, right? But it's going to be 5 milliliters, right? Okay. Why? Because of the adhesion of water. Water molecules in this point. So let me show you. So water molecules in this point are going to be like adhered to the tube, okay? So they will be using their adhesion property, but the current volume is going to be 5 milliliters, right? And that can happen with different things, right? Okay, so water is described as hydrophilic. Hydro means water, philic means love in certain ways. So it means that they are attracted by water, right? So there is another term that is called hydrophobic. And in hydrophobic examples, you can find oil. Oil is not attracted by water and is hydrophobic, right? And in fact, both have different densities. The densities for both are different. The density for water and for oil is going to be different, right? So it is. Okay, they are completely different. Okay. So in this table, we see the physical properties of water in air at 20 Celsius degrees. Remember that air is basically formed by different elements. So in certain way, it's not a pure substance, right? So we have the physical properties of water and air at 20 Celsius degrees and 1 atmosphere of pressure. For air, molar mass is weighted average because it is not a pure substance, right? Since molar masses can only be calculated for pure substances. So here we have, for example, the density of water that is 998.21, but in air is going to be more. It's going to be, sorry. So for water is 998.21, in air is 1.204. The thermal conductivity in water in this case is 0.598. In air is 0.02154. Specific heat capacity, 4.184. In air is going to be 1.007. And the dynamic viscosity is 1.002 times 10 to the minus 3, 1.825 times 10 to the minus 5. So the difference are notorious. Okay, so the difference are notorious. Okay, so the black-throated loon that is known as Gavia arctica in the left, and the ringed seal that is called as Pusa hispida, right, are going to use the water properties to survive in these hostile environments. Okay, so in ice, for example, the water molecules are hydrogen bonded, as you can observe here in the Pusa hispida's case, right? And are hydrogen bonded in an open tetrahedral lattice, which makes ice less dense than liquid water. In fact, there is an experiment to measure the water volume, but when the water is in solid state, I mean in ice. Right? So remember this, guys. Cohesion refers to the attraction between water molecules themselves, but adhesion refers to the attraction between water molecules and other substances or surfaces. And this extension is a common problem that my students face, right? So here, for example, we have the Xylem vessel, right? So the cohesion in this Xylem vessel, I will illustrate this. This is the Xylem vessel, right? Xylem vessel. Okay, so the cohesion is going to be between water molecules. Okay, between water molecules. Between water molecules is known as cohesion. But when those water molecules crash the walls of the xylem, there is going to happen something that is called adhesion, right? So the water molecules will adhere to the xylem walls, right? And this is called adhesion. Really important to comprehend that adhesion requires the use of an external body, right, or substance or surface. But a cohesion is between molecules, right? Intermolecularly speaking. Okay, so we'll look closely at how the oxygen and hydrogen atoms share the electrons. So this is the electron cloud that is produced between these two atoms, and the bonding electrons are going to share evenly between the hydrogen and oxygen atoms, right? Oxygen attracts to the electron a little stronger because of its electronegativity, and this uneven sharing causes small charges to develop, right? Negative and positive charges. And the attraction between the partially charged atoms is basically given in this case, okay? Also, we have to talk about the capillary action. So water's adhesion to capillary walls in soil plant cells walls allows it to move outward against gravity. So this process is known as capillary action, right? So the capillary action is vital for plants to absorb water from the soil, especially during dry conditions. The cacti, for example, they absorb water and they store the water in their thorns, right? So in dry conditions, for example, due to the capillary actions, the water can be stored in the cacti, in cactuses. Okay, this is another example of a really famous experiment that we can perform with students. And in this case, what I'm using is basically, you can use like a napkin, something like that. You can use food coloring, and then you're going to observe how the water molecules will be using the capillary action to be in the other side, right? And they are also using the adhesion and hydrogen bonds, all of these. Right? So water, as we have said, is the universal solvent. Water is an excellent solvent because of its polarity, right? So an example are ionic compounds like sodium chloride, right? Sodium chloride. And sodium chloride, if you pour it, this is table salt, table salt. If you pour it in water, you're going to have a solution where water, the salt is going to be the solute, and the water is going to be the solvent. A solution is basically formed by solute and the solvent. And water basically dissolve most of the 60%, more of the 60% of the compounds that exist, right? So molecules can dissolve and become more chemically reactive when we use water, right? So hydrophobic substances that are called non-polar because they don't present poles, negative or positive charges attracted by water, right? They do not dissolve in water and they are repelled by it, which is significant for the structure of cell membranes. For example, in the phospholipids, you find a part that is basically hydrophobic because it does not need water, so it requires other conditions better than having water. Okay, so the key properties here are that water can also include buoyancy, viscosity, thermal conductivity, and specific heat, right? It also has a great specific heat capacity, right? In fact, you can boil water at 100 Celsius degrees, and that's a lot, right? So water can store a lot of thermal energy or heat energy. It also refers to the water as a bridge to store thermal energy, right? Also, we have viscosity, right? And viscosity is basically the water's resistance to flow affects the movement of organisms and nutrients in aquatic environments, right? So the more viscosity we have, the slower we're going to be, right? And finally, we have the thermal properties, and this is what we call the triple point. In the triple point, you're going to find different states such as a gas, right? Gas state, a solid and liquid state. They will encounter one to each other here, and this is what we call the triple point. This is a diagram to show the states of matter, right? So water requires a lot of energy to change the temperature states, to change the temperature in aquatic habitats and supporting diverse life forms. All right, basically that is like the water class for today. And the aquatic organisms, like these animals you observe here, such as the black-throated loon and ringed seal, rely on water's properties for hunting, breeding, and survival. The ability of water to support buoyancy allows these animals to thrive in their habitats, while its high specific heat capacity ensures stable environmental temperatures. So water also plays an important role in keeping our temperature. And in fact, when we go and exercise, our temperature doesn't change a lot. And also, when you go to the doctor, for example, the doctor is going to measure your weight, most of your body is going to be weighting due to water. So water is playing a fundamental role. At the same time, it helps you in your homeostatic process, right? In your homeostasis, right? That is the way that our body regulates ourselves. Okay, there is a theory, right, that talks about the extraplanetary origin of water. So it says that water was originated in exoplanets, right? It's a well-supported hypothesis that suggests Earth's water was delivered by celestial bodies, such as asteroids and comets during the planet's formative years. So here is basically a breakdown of these key concepts, illustrated with example of two animals that inhabit both aquatic and terrestrial environments. The black-throated loon, that is the Gavia arctica, and the ringed seal, that is the Pusa hispida, right? So in the extraplanetary origin of water, Earth formed about 4.5 billion years ago, right? In a hot environment where water couldn't exist as a liquid. And the conditions necessary for liquid water only emerged after the planet cooled, likely after water was brought from external sources. Likely after water was brought from external. Likely after water was brought from external sources, right? Source of water, they could be asteroids and comets, right? And their researchers suggest that asteroids, especially carbonaceous, especially carbonaceous chondrites, may have delivered substantial amount of water in their planet. And these meteorites can contain up to 28% of water and have isotopic conditions similar to the Earth's oceans. Okay. Also, the hydrogen isotopes, such as deuterium, that is hydrogen-2, and tritium, that is hydrogen-1, specifically, and these meteorites can match the isotopic composition found in Earth's water, supporting the hypothesis that these bodies contributed to the formation of Earth's ocean. Also, we have the meteorite impact. So the asteroid impact contain water molecules, right? And upon this, the meteorite impact, so the meteorite contained water molecules, right, that were released after this scratch against the Earth, right? So this water vapor can then condense, contributing to the formation of the oceans. And finally, we had a cool down phase. As the Earth cooled, water vapor condensed into liquid form, allowing for the establishment of oceans and other water bodies, right? And that's basically the history and the theory we're going to be approaching in this course of water. See you guys, I hope that this has been completely useful to you. I know that there is a lot of information there, but remember, you got to continue moving straight forward. See you guys.